This video is for my Algebra 1 class, is over Lesson 84, Identifying Quadratic Functions. So I may want to take a moment to pause and copy down the chart. So ladies and gentlemen, before we dive into quadratic functions in particular, we're going to walk through a few different types of functions that we can come across. So in particular, we're looking at polynomials. And so degree 0, 1, 2, 3 is where we're going to limit ourselves today. So degree 0 remembers that the highest exponent on any variable is a 0. So, well, 0 is just going to make that variable disappear, which is why our equation is going to be of the form y equals a, where a is a constant. So if you have a situation like this, anytime a equals a number, remember that this produces a horizontal line. So examples of this would be the x-axis. Y equals 0 is actually the x-axis. Or we could say y equals 5, which would be a horizontal line going through the y-axis at 5. A degree 1 polynomial, degree 1 function, would have a 1 as the highest exponent on any variable. And so typically we write these in the form of y equals mx plus b. We think about our slope-intercept form. For a little bit of consistency's sake, though, you can think of your m here as being kind of like a. So it's almost like this equation right here graduated. The a got multiplied with an x, and then we added on a b. So this then, of course, y equals mx plus b is the general equation that we use for a line. So we would call this kind of function a linear function. It's graphing a line, so we would call it a linear function. So examples of this would be, if we just make things real simple, y equals x. Or a little more complicated, y equals 5x. Or y equals 5x plus 10. Each of these would be of this form. Here, m is 1, b is 0. Here, m is 5, b is 0. Here, m is 5, b is 10. Moving on, degree 2 means that the highest exponent on any of my variables is a 2. And so it's almost like this ax plus b has graduated as well. And so the x is turned into an x squared. The b now has its own x, and now we're adding c. So if you find an equation of this form, a function of this form, we call this the quadratic. This is a quadratic function. Quadratic function. And so examples of this would be, if we keep things real simple, just y equals x squared would be a quadratic function. Or y equals a negative 2x squared plus 5. So notice we can be missing the x term and the constant, or we could be missing just the x term. That's okay. I could have y equals 3x squared plus 4x. So instead we could be missing the constant term. That's all right. Y equals x squared plus 10x plus 25. Could have all three terms. So, but the most important thing here is it's got to be degree 2. So the one thing that can't be missing is the x squared term. As we move down to degree 3, so the highest exponent is degree 3. So again, it's like all of these just got promoted up. So now it's an ax cubed, it's a bx squared, it's a cx, and now we got a plus d. So if we see something of this form, this is what's called a cubic function. And so just like with the quadratic, the most important thing is that the cubic term is still there. The x cubed term is still there. So I could have, if I keep things real simple, y equals x cubed. That'd be about as simple as I could get that. Or A little more complicated, y equals a negative 5x cubed minus 7x. So here we're missing the quadratic term and the constant term. I could have y equals 16x cubed plus 9x squared. So we're missing the linear term and the constant term. Or I could have y equals x cubed plus 3x squared plus 3x plus 1, where I have all four terms there. So these are all cubic functions there. Now, a quick word before we move on. This right here, and this right here, these are all what's referred to as the parent function. So the parent function is basically if we take the general form and we simplify it down as much as we can. So the most important thing in each of these is that we have that term that makes the degree. So I can't get rid of my x cubed, I can't get rid of my x squared, I can't get rid of my x here. But you could get rid of all the rest of this. Turn b, c, and d all into zeros. And then make this simple by making a1. And it's just y equals x cubed. Likewise, down here, get rid of those, make b and c zeros, make a 1. There you go. So those are the parent functions. And we're going to do a little bit with the parent function. It's going to reveal some things for us in just a second. So ladies and gentlemen, when it comes to quadratics, the thing we're going to focus on here is the quadratic equation, or quadratic function, it can be called as well. Written in function notation. Remember, this is f of x. So f is just labeling what we're doing. We could also have a g of x or an h of x or whatever. And then in parentheses, this is just our input variable. This is identifying what is the input variable. And so f of x equals a x squared plus bx plus c. And as we said before, we need that x squared to still be there. So a cannot equal 0. All the rest of them can equal 0, but a cannot equal 0. If a equals 0, then my x squared term goes away and it's no longer quadratic. So the parent function here, let's go ahead and grab our highlighter here. Actually, while we're at it, highlight linear, quadratic, cubic. Those are vocab terms. So our parent function, remember, is we just make this as simple as we can. And we're going to go ahead and graph this, and this is going to reveal some things about quadratic equations, quadratic functions. So to graph this, we're going to make a table of values. Remember, ladies and gentlemen, to graph anything, all you need is enough points that you can find the shape of the graph. So we're going to start with -3 for our input, and we're going to work our way up to a +3. So a -3 squared is 9, a -2 squared is 4, a -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So quickly, one of the things that I notice is that left and right, it's not changing that much, but up and down, it certainly is changing a good bit. The other thing I notice here is look at all your y values. We do have 0, but then we have a bunch of positives. So there are no negatives, and that shouldn't be too much of a surprise. So when I make my graph here, I'm going to put just a little mark here, just kind of say like that's kind of the corner of it. And I'm going to count down. We know we've got to go up to 9, and then I want to leave a little extra space. I want to go down to 10. So I'm going to go down from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces, and we'll start our x-axis there. And then for my x values, I'm going a total of 3 from 0 on each side. So that's a spread of 6. So let's go one more on each side. So let's go 8 across. So 1, 2, 3, 4. That'll be where my y-axis will be then. 1, 2, 3, 4. And so that gives me my 3 on each side with one more just for a little extra wiggle room. Now I'm going to bring this up. Remember that little spot we made to tell us where kind of corner of the graph was? So I don't have to count. I've already counted that out. And then since we're not really going into the negatives, I'm just going to go 1 down. Just 1. That's all we need. Now, from here, let's plot our points. So we have a -3, 9. I have a -2, 4. A -1, 1. 0, 0. 1, 1. 2, 4. And then 3, 9. And so if I draw a curve through my parent function here, make sure that kind of curves there. We've just discovered the shape of this. So the shape is what's known as a parabola. Kind of looks like a U. It's a parabola. And it turns out that parabolas, as hopefully you can see here, are symmetric. So I got a y value of 1 there, y value of 1 there, y value of 4 there, y value of 4 there. These both have a y value of 9. If we were to continue, both -4 and +4 would have y values of 16. So we have a line of symmetry. A line of symmetry. And now for my parent function, it's just the y-axis. However, this is not always going to be the case, so I'm going to do you a huge favor here. Your line of symmetry, in general, is going to be the vertical line whose equation is x equals -b over 2a. Now, what does that mean? Well, b is the coefficient of x, and a is the coefficient of x squared. So if we apply that in this case, because I don't have a b term, that means that b is 0. So -0 is just 0. My a is an invisible 1, so 2 times 1 is 2. So this is really 0 over 2, which is 0. So x equals 0 is my line of symmetry. Well, that's the y-axis. X equals 0 is the y-axis. The other thing that we discover here is that there's a special point right here where the line of symmetry hits my parabola. And this is called the vertex. And I'm going to do you another favor here. Well, we can plainly see that the vertex this time is the origin. And in general, if you can find two symmetric points, you can just go halfway between them and you know where at least the line of symmetry should be. And then from there, use some algebra and find out what your x and y value should be for your vertex. But in general, since it is on the line of symmetry, you know your x value is going to be a -b over 2a. That will be the x value of your vertex. To find the y value, we're going to plug in to our function, so into our function, that x value. And that's your vertex. So let's try this out. And because I'm running out of room, I'm going to go to the back here. And for our next example, let's take a look at f of x equals a negative x squared minus 4x minus 4. All right, so first of all, a here is the coefficient of your x squared. So this is just a negative, which really means it's a negative 1. B is the coefficient of your x. Now remember, minus gets treated as a negative. So this is really a negative 4x. So B is a negative 4. And then C is the constant. Now the formula says plus C. So think of this as addition. If this is a minus 4, what are we really adding? We're really adding a negative 4. So this means that my line of symmetry, and we're going to abbreviate that SEM, line of symmetry is going to be x equals a negative b. So there'll be a negative 4. So in other words, those are going to cancel over 2a. So 2 times, and my a is a negative 1. So that is 4 over negative 2 or negative 2. So this is going to be symmetric around negative 2, the x value negative 2. So when I make my table of values for this, I'm going to take advantage of that line of symmetry there. And it's typically nice to get at least 5 points when you're making one of these. The more points you can get, the better. So what I'm going to do is I'm going to find 7 points again. I'm going to graph at least 5 of them, but I'm going to find 7 of them. And I'm going to put my negative 2x value in the middle here. So negative 2, and we're going to go a little bit on each side. So negative 3, negative 4, negative 5. Down here I'll go to negative 1, 0, positive 1. Now watch this. This is real nice here. Remember that it is symmetric. Sorry, I can't write apparently holding both of my writing utensils. Let's try that again. That this is symmetric here about that negative 2. So let's just start by plugging negative 2 in. So a negative 2 squared is 4. So that's going to be a negative 4. Then a negative 4 times a negative 2 would be a positive 8. So we got a negative 4 and a positive 8 makes a positive 4. And so then a positive 4 minus 4 is 0. So that's my vertex right there, is negative 2 comma 0. Now remember, it's symmetric here. So let's go, I think it'd be easier to plug in negative 1 than negative 3. So let's just plug in negative 1. So if I plug in negative 1 squared is 1, but then it's going to become negative. So negative 1 again. Then over here, a negative 4 times a negative 1 is a positive 4. So negative 1, positive 4 makes a positive 3. And then a positive 3 minus 4 is a negative 1. So this point here will be a negative 1. But remember, it's symmetric. So if going 1 unit to the right produces a negative 1, then going 1 unit to the left will also produce a negative 1. Our next one should be really easy. 0 squared is 0, and there is negative 0 is just 0. Negative 4 times 0 is 0. So 0 and 0 makes 0. But then minus 4 would be a negative 4. Well, if that's a negative 4, then this is a negative 4. Hopefully you're seeing how easy that can be. All right, plug in 1 now. So 1 times anything is itself. So 1 squared is 1, and then it'll become a negative 1. A negative 4 times 1 will be a negative 4. So a negative 1 and a negative 4 makes a negative 5. Minus 4 makes a negative 9. Well, since it's symmetric, if that's a negative 9, then that's a negative 9. And so we notice kind of a similar setting here to last time. But what I'm going to do with this guy here is I'm going to have this go down instead of up. So I'm going to just kind of skip down a point here. And I see this negative 5. So I want to go at least 6. 2, 3, 1, 2, 3 before I make my y-axis. So I got a little extra room beyond that negative 5. And then let's just go ahead and, in the spirit of symmetry, go ahead and go 6 the other way. Now we're not really going into the positives this time, so I'm just going to go 1 up, but then I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then just an extra 10 down. And I would recommend that you start with your vertex. So negative 2, 0 is my vertex. And then going negative 1 takes me down here. So 1 to the right is there. So 1 to the left should be right there. Sure enough, it is. Negative 3, comma negative 1. If I go 2 to the right, so when x is 0, y was negative 4. So when I go 2 to the left, we should also be down at negative 4. Well, that's negative 4, comma negative 4. And then finally, when I go 1, 2, 3 to the right, that's where x is 1. This is all the way down where x is, or y is negative 9. And so then if I go symmetric to that, I should have a negative 9 there, where x is negative 5. Now, draw your parabola, kind of that U shape here. Nope. That started curving over too much, so if we make a mistake, we just erase it. That's why we do everything in pencil. And ta-da, there's my graph, there's my parabola. So, ladies and gentlemen, notice that this parabola is opening upward, but this parabola is opening downward. There's a really easy way to tell when that's going to happen. You see, ladies and gentlemen, if we consider x squared, we consider x, and we consider a constant, okay? Which of these is the most powerful? Well, it's certainly not the constant, because no matter what x is, the constant will always be itself. If you go with the linear term here, the x term, then you're going to take whatever your coefficient is and just multiply it by a single x. But if you take your quadratic term, you're going to take whatever that coefficient is and multiply it by x twice, x squared. So what's going to happen is as our values for x start going more and more into the positives and more into the negatives, it's this quadratic term that's going to kind of take over. It's going to have the most influence on the shape of the graph, what's going on with the graph. These guys are going to become nearly irrelevant fairly quickly. Not completely irrelevant, but nearly irrelevant. And so this really becomes the most important thing. And because of that, this A has a controlling power. And its controlling power is whether the graph will open up or down. So consider here in this parent function, our A was a positive 1. But over here, our A is a negative 1. So what I hope that you're kind of grasping onto, and I'm going to go ahead and spell it out just in case you're not, is that the value of A will control whether or not it opens up or down. So parabolas open up when A is positive. And open down when A is negative, when A is less than 0. So if you have a negative leading coefficient, that A is negative, then it's going to open down. Expect to open down. If A is positive, it will open up. So just looking at a glance at the equation, you should be able to tell if it opens up or down. So with that being said, we're going to take a look at one more example, and then we're going to call it good for today. So this one, a little bit different. Y plus 3x equals x squared plus 1. So first of all, you'll notice that this is not written in proper function notation, proper form, standard form. And so we've got to do a little bit of algebra here. So we want equations that say y equals. So the issue here is I don't want the 3x on this side of the equation. So what we're going to do is we're going to subtract 3x from both sides. So I got a 3x here. Now over here, if we had an x term, we'd line our minus 3x up with that x term. Since I don't, I'm just going to kind of put it over to the side. And so now these guys will cancel. That'll leave me with just y. Now I am going to put this in standard form, though, as I rewrite the equation. So I've got x squared minus 3x. That's my linear term. So my quadratic term, my linear term, and then my constant term, plus 1. And now we're ready to go. So I would do a quick analysis here. So my leading coefficient, my a, this time, is 1. So right there, we know it's positive. We know that this is going to open upwards. My b is a negative 3. Remember to treat subtraction like a negative. And then finally, c is a positive 1. So here we go. This means that my line of symmetry is going to go through x equals a negative b. I'm not going to bother doing the negative thing this time. I think you all know a negative 3 is just a 3. So we know it's a 3 over 2a. Well, again, I'm not going to bother writing 2 times 1. We know 2 times 1 is 2. So another way of looking at this is going to go through where x is 1.5. 3 over 2 or 1.5. Or you could say 1.5. I'm going to do 1.5 though. So when I make my table of values, I'm going to go x and y. And I'm going to put 1.5 in the middle. So everything, remember, is going to be symmetric around this. Oops, sorry, I got to slide that up there. My apologies. So everything's going to be symmetric around the 1.5. So what I'm going to do here is I'm going to go, well, halfway to the right. Just 1/2 step to the right. Go 1/2 step to the right and I'm at 2. If I go a half step to the left, I'll be at 1. From here, I'm going to go a full step to the right, so that'll go up to 3, which means I should go a full step to the left, 0. I'll go one more full step to the right, which means I should go one more full step to the left. So make sure those are symmetric x values around 1.5, and then your y values should match each other. So now let's go ahead and start plugging things in. So 1.5 squared is 2.25. 3 times 1.5 is, negative 3 times 1.5 will be a negative 4.5, and then plus 1. If you put all that together, that'll be a negative 1.25. So remember, ladies and gentlemen, that there is your vertex. That's your vertex right there. Now, let's just plug in whatever we think would be easier. I kind of like the smaller values here than the bigger values, so I might actually plug these in this time. So we plug in 1. 1 squared is 1. Negative 3 times 1 is negative 3, so this is basically 1 minus 3 is a negative 2, plus 1 is a negative 1. So if that's a negative 1, then this is a negative 1. Plug in 0, that'll disappear, this will disappear. It's really just going to be 1, positive 1. But if that's a positive 1, then its mirror image will also be a positive 1. And then finally, if I plug in a negative 1, negative 1 squared is 1. And then a negative 3 times a negative 1 would be a positive 3. So 1 plus 3 plus 1 is 5. And over here, 5. Now, I might decide this time, I see the 5s, I got a 4 there. I might just decide this time, let's just go 6 in every direction for our graph. I think we should have room for that. So 3, 6, 3, 6, 3, 6, 3, 6. And then we graph. Again, it's kind of nice to start with your vertex. So 1.5 and comma negative 1.25. So 1.5 and then a negative 1.25, or about a negative 1/4. So that's my vertex right there. It's going to be all symmetric around that point right there. Now let's plug that in. So if we go over to the 2, it was a negative 1. So if we go over to the 1, it's also a negative 1. If I go over to 0, 0 gives me 1. So symmetric from that should also be a 1. Finally, if I go over negative 1, it goes all the way up to 5. So if I go symmetric from that, 4, 5 is my other point. And draw my curve through those points. And there's my graph. And that, ladies and gentlemen, is the end of our lesson.